Hi everyone. Now in this lecture we will discuss about one of the most defining characteristics of a cellular system, that is mobility. Okay, so which means you have wireless connectivity even when the device is moving with a very high velocity. Okay, velocities of the order of few tens of kilometers per hour to the lower end of hundreds of kilometers per hour. Okay, so that's the general speeds with which they are designed to work at such high speeds. Even when you are moving on a train, you should still have mobile connectivity. So what is the fundamental problem when you are moving? So if you recall, in the previous lecture we discussed that in a cellular system, each you are going to divide the whole region into what we call as cells. We are just going to divide them into cells. Now let's assume that your mobile device or the user was static, meaning he or she was within the cell, he is never going outside the cell. Okay, then there is nearly no problem for mobility. Okay, so that's one very important factor to understand in the cellular system, is that there is no requirement for mobility. Okay, but the way in which cell phones are designed is that a user can move from one cell to any cell anywhere at a very high speed and still have the connectivity. So that's the most important design aspect of a cellular system. So how is this accomplished? So for example, if a cell phone, if the cell phone is in one cell, it will normally be connected to one base station. So now when the cell phone is going to enter into another cell, it can no longer be connected. See, I can always ensure that okay, this cell phone is connected to the main base station, but the problem is if I want this base station to be connected to this cell phone, then the transmit power has to be increased. So that's the only way I can maintain connection, because otherwise your signal power, if you recall, there is something called sensitivity. If your signal power becomes less than sensitivity, then you will lose the reliable communication. The quality of communication is lost. Okay, if you recall, how did we compute sensitivity? We computed it from SNR and all that. So now the problem with the cellular system is that you should actually always hand off, ensure that the signal to noise ratio or the sensitivity, the signal power received by the cell phone has to be of good quality. Okay, so which means the cell phone now has to be served by a new base station. So that's the only way this can be accomplished. Now if the cell phone again keeps moving here, a new base station should again serve the cell phone. So now the cell phone is essentially moving from one base station to other base station. So previously there was a connection between one base station. When the call is going on, one base station was connected to the cell phone. Now the connection has to be established, but now through a different cell phone, if the call has to persist. Okay, so this phenomenon of shifting the call or shifting the connection, this is a wireless connection. There is no wired connection, it's a wireless connection from one base station to the other base station, is what we call as handoff. Okay, so how is it done? We should do it in the most efficient way, such that there is no call drop. Your signal call should not drop. So now what is one of the main reasons why should we do the handoff is that the previous base station will be using certain frequencies, say F1. This base station adjacent to that obviously is going to use a different frequency, because you have to keep in mind, in an FDMA system, orthogonality is ensured through using frequencies. Different frequencies means there is orthogonality. So which means the adjacent base station has to use a different frequency. Otherwise, you will end up transmitting data in F1 and it will cause a lot of interference. Right? That's one of the reasons why cells which are close by normally will be in a cluster, and those cells has to use different frequencies. So now when this mobile station is going from one base station to the other base station, the carrier frequency with which the modulation was taking place will also change. Okay, so previously if the carrier frequency was F1, the carrier frequency will now become F2 for the second base station. So there are a lot of changes which are taking place. So which means when these changes are taking place, the transition should be smooth. Otherwise, we can have a probability of call dropping. Okay, so this part of the lecture will focus on what are the different strategies of handoff that is present, and towards the end I'll also discuss what are the strategies that is which I did not discuss this in the lectures in CDMA. Very briefly we'll discuss what happens in a CDMA system. So first, before we start the principle of handoff, first we should understand, how does a cell phone know that it is moving away from a base station, or how does a base station know that a cell phone is actually moving away from the base station itself. Okay, so for this, both the cell phone and the base station, in the past, in the beginning, base station used to do all the calculations. So base station estimates what we call as RSSI, received signal strength indicator. Okay, it computes a received signal strength indicator. So meaning it somehow computes what is the power levels that is being transmitted by the here in this case what I am talking about is the computation made by the base station. The base station tries to estimate the power that it is going to receive or it is receiving from a cellular phone. Okay, now based on that now if your received signal strength is really low, it's very low, then it is going to understand that okay, it's either moving away from me, moving away from the base station, okay, or there is an obstacle in between. So we'll very briefly come to that, how does this problem is resolved. But now the question is, how does it compute this received signal strength? Now what I have shown here is a typical receiver of a base station or an ADC. The receiver will look the same. The receiver architecture will look essentially like this. So your signal is first received by a block called known as amplifier, which will just amplify the signal because your received signal power will be very low for us to process it, for the circuits to process it. So first you have to do amplification. Then the next step is demodulation or down conversion. So I'm going to multiply it with a carrier called carrier frequency, or I'll call it cos omega 2t. Okay, and then translate. So this data is going to be centered around, if I say frequency f1, it is going to be around frequency f1, the carrier frequency f1. So first what I'll do is, let me just multiply it with the carrier frequency fc1. I'm going to multiply this signal with the carrier frequency fc1. So now once I multiply it, you will get two components, fc1 plus f1 and fc1 minus f1. Usually the plus f1 component we'll neglect it, we'll ignore it because there is a filter which will filter it out. Okay, so eventually I have to bring whatever data is present here to DC, and that can be accomplished using a direct conversion receiver. It will directly convert the high frequency content to low frequency content by multiplying it with a carrier frequency of value 2 pi f1t. Okay, but instead of doing that, there is something called super heterodyne receivers or intermediate frequency receivers, IF receivers. What do? They multiply it with two frequencies, fc1 plus fc1 and fc2. The frequencies are chosen such that fc1 plus fc2 will be equal to f1. So you do it in two steps. It has some advantages. Why we do that in two steps? It has its own advantages. Okay, so the first step, I'm going to compute and translate all the signal to a frequency fc1 minus f1 or f1 minus fc1. It can be anyway. Okay, whichever is greater. So here I'll assume since f1 is greater, I'll assume f1 minus fc1. Okay, then what we do is this is called as an intermediate frequency filter or IFF. So this filter will contain energy only around the intermediate frequency, which is nothing but f1 minus fc. Now you can directly compute the power in this. So once you have a sampled signal, once you compute the sample the signal, the signal power can be easily estimated using the digital samples. Okay, it can be easily estimated. So I mean, one quick way is doing summed over. Once you sample it, IFADC samples it, you can actually have the data, digital data, discretized data. Then you can simply do x of k the whole square, summed over k to whatever number of samples you have picked. Some say m or the variable can be, I'll use a different, some p number of samples. So you have to square these samples and find the energy. Okay, and if you average it, you get the received signal power. So normally you will have a threshold level. What should be the threshold? If your received signal strength is lower than that, then you know that okay, you're really the mobile phone is moving away from the base station. Or the computation is also sometimes performed at the baseband. So this is called intermediate frequency ADC. It's also sometimes performed at the baseband ADC, which means after converting the signal all the way to DC, the center frequency was initially f1 for this. Now you have shifted this all the way to low frequencies. Again, demodulation will do that for us. We can shift it to low frequencies. Now once you shift it to DC, again in a similar way, you can sample the signal. Once you have digital samples of the signal, you can then compute the energy of the signal. Okay, or power as well, you can compute it. So here it will be energy, because it's a finite duration signal, we will compute its energy. So that way we estimate the energy, and that's how you get what you call RSSI. This is all done digitally, because output of ADC is a digital signal. You can compute this power digitally. Okay, now using this RSSI, handoff is normally performed. So for example, when your mobile phone is moving from one base station to the other base station, your base station will now compute the power of this mobile phone. The adjacent base station will also compute the power of this mobile phone. Okay, two base stations will compute it. We'll see how the handoff is initiated. So typically what happens is that your two mobile base stations here, I'll call it BS1 and BS2, both of them have computed the powers of the cell phone. Okay, now it turns out that BS1 is now seeing, okay, the power is gradually decaying over time. Okay, you are now plotting the graph of power with time. Okay, so when you are plotting the graph of power with time, it's slowly decaying. So you know that now the object is moving and it's moving away from you. So that's an indication, meaning if your power is decaying with time, that's an indication. You know that power is going to reduce with distance. If your distance is increasing with time, which means that it's moving d equals bt, where v is the velocity of the object, t is the time. Your distance is increasing, so which means your radiated power is also decreasing over time. Okay, so that's an indication. So now we know that the power is reducing. So now then these two base stations will be connected via a backbone mobile switching network, MSN. Now this MSN will tell, okay, now why don't this information will be broadcast to the MSN, and MSN will quickly take a decision. Okay, now the cell phone is actually going to come into cell 2. So this is cell 2 and this is cell 1. So why not base station 2 take over? So then base station 2 will take over and base station 1 will stop transmitting the data. Okay, so this is called a handoff. Now the handoffs can be generally two types. One is make before break. Okay, so generally we prefer make before break connections. So meaning base station 2 will make a connection with the cell phone before base station 1 breaks it. Okay, so that's called as a make before break connection. If you do a break before make connection, then you will normally have a call drop. So you shouldn't do that. So then the base stations use what we call as a make before break approach. So first a connection is made between base station 2 and the cell phone, and then you will break the connection to base station 1. Okay, so this is one way of doing handoff. So you just have to find a threshold. If you know that, okay, look, my signal power is here, it's been reducing now and it is approaching the threshold. Okay, threshold can be sensitivity also. It can be sensitivity of the receiver. If the signal power goes below the threshold or sensitivity, at this point you will have no call because your signal power is lower, so your cell phone will no longer be able to faithfully give you the conversation at all. So it's as well as no conversation is taking place. A call will be dropped. Okay, now this is the way it's normally done. Now there are some problems with this measurement. Sometimes what might happen is a sudden obstacle can come in between the phone and the tower, okay, to the cell tower, and that obstacle can move away after some time. A few seconds later or a few moments later, the obstacle can move away. It maybe it's a moving vehicle and a very large truck, a very heavy truck carrying probably a lot of metal objects in between, where there was a path between, let's say there was a path between you and the base station, and a huge truck comes in between. So after a few seconds it goes away, your signal power will return to normal values. So when you are measuring the signal power, you will actually, when you are measuring it, you will see normal values, suddenly there will be a dip and then it will go back. Okay. So normally what we do is we do an average. We actually compute, we take power readings for a longer duration, okay, for a certain interval of time, and then make a decision. So when you are doing that, you will know if the power returns back quickly after some time, then you know, okay, this was just an obstacle. The object is not moving away. Or the cell phone can just move here and then return back. You know, it can return back, even then the signal power can increase. So then you will know that, okay, the cell phone is returning back, so I don't need to do the handoff. Okay, so all this information can be provided if you can estimate RSSI over time. RSSI is measuring power, received power as a function of time. If you can know this, then you can get a lot of information about the device. If the received power is decaying very fast, if your received power is decaying much faster than this, then you know that your device is moving at a much faster rate. Okay, so you will know that your device is actually moving at a much faster rate. So that's about very basic, at a very basic level, how handoff is performed. So it mainly is performed depending on a thresholding basis. You have a threshold. If a signal power is reaching the threshold, then the base stations both the base stations already are doing the computations and they are relaying it to the MSN mobile switching network. Okay, so right now the current base stations do a lot more processing. In the past, the first generation, a lot of intelligent decisions were made at the mobile switching network. Okay, so base station, in fact the calculations were done, a lot of calculations, the computations were performed by the base station itself. Today a good deal of calculations are performed by the cell phone itself. Okay, so now we'll see how a basic handoff is performed. So like we said, we keep measuring the receive power as a function of time, or RSSI. RSSI is nothing but the receive power. You keep measuring it as a function of time. Now what you do is, this is the minimum power level at which, below which communication can no longer take place. Okay, so that is something you are aware of. So then you will add a delta to that and say that, okay, look, if my signal power reaches this level, then that's what I would call as a handoff threshold. Okay, at this point itself I'll initiate the handoff, because if I wait for some more time, the signal power can go lower than Pmin and I might lose the call. So instead, there is something called handoff threshold. So you will assume the minimum power level for good reliable communication, and you will add a delta to it, where delta is the handoff threshold. So handoff is initiated the moment your received signal power R is equal to this. Okay, delta plus Pmin. Now if let's say I don't initiate, so for example there are several, we'll come to the problems. Now let's say I don't do that. If I don't initiate at the handoff threshold, or if I'm waiting, maybe if the device is moving much faster, suddenly the power can decay much faster and it can go even lower than Pmin, and suddenly I might have call termination at this point. Okay, so that's the problem we have to avoid. So again, if the call is terminated again, the user either have to make a call again. Okay, there is no other way the cell phone will be reconnected back. Okay, the user has to make the call again. So now that's why doing the transition at the right point is very, very important. So I have shown here two graphs, the power levels of, this is the power level recorded by a base station as a function of time. So the base station here, I'll call it base station A. So this is A, base station A, and this is base station B. So now if you see the base station B is also, if you see base station A, the signal power level is constantly decreasing, and then if I don't do a proper handoff in this case, that's what I'm showing here. I've shown here an example where the handoff is not done properly. So meaning at this point, the transition we didn't initiate the handoff. We waited for some time, the handoff was initiated poorly, so the call dropped. The second one here, this shows the received signal strength. Okay, so this is the received signal strength of the mobile phone. I'm sorry, I just told the received signal measured at the base station. So this graph just shows the received signal strength by the mobile phone. That's it. Mobile phone is a function of time. Okay, so what happens is that the received signal strength obviously keeps reducing because you're moving away from the base station. But now at this point, handoff has already happened. So you have initiated the handoff at the right point, which is at the threshold point. When the signal goes lower than the threshold, we suddenly initiated the handoff. Now at this point shown here, handoff has already happened. So the moment handoff has happened, now the cell phone is now going towards the tower B. Okay, so which means your signal power will start increasing. Okay, so your signal power will start increasing, and it will actually keep increasing further. So that's what is shown here. Now this is not foolproof, it has its own problems. The choice of delta is extremely challenging. So the threshold for handoff has to be chosen very, very carefully. If I choose a large handoff threshold, we might have false handoffs. Okay, because your handoff is so large that you might start handing off at a much earlier time than necessary. You can actually end up having false handoffs. Okay, or if your handoff is too small, which means you are very, very close to the minimum power level, then by the time the handoff is initiated and by the time you make a change, your signal power would have decayed significantly and the call might be terminated as well. So choosing the handoff threshold is actually very important. Okay, so that's what I've explained here. Okay, so now there are two things which is happening. One, there are two decisions which are made. One, someone has to measure RSSI, received signal strength indicator. So that has to, received signal strength has to be measured, and the calculations has to be performed. Whether it's lower than the threshold or when should be initiated threshold handoff and all that, these decisions also has to be made. So now the base stations are pretty computationally efficient now, so they do a lot of calculations. In fact, half of these calculations, the received signal strength calculations, are all performed by the mobile phone itself. and finally it relays the data to the base stations. Okay, mobile phone itself can do a lot of calculations right now. But as I said, in the first generation of systems, the first generation, your base stations used to do all the calculations. Okay, but as we move to digital communications, which is the first generation was an analog FM based modulation, and it was an analog communication wireless system, a cellular system. The second generation was what we call GSM, which was a digital communication system, and we said it employed TDMA. Now when it was employing TDMA, what happened was that we said in a TDMA system, you are given a slot, you can only transmit in this slot. In the remaining slot, the data is buffered, which means there is no transmission or reception happening in that slot. Okay, the data is just whatever data is generated at the mobile phone is getting buffered, stored. Okay, so but in this duration, now that there is no data transferred in a GSM or TDMA system, you can actually do all the handoff calculations, and by the time when your next slot is going to come, okay, you might, for example, let's say you are in base station A and you are in base station B, you are moving towards base station B, and you are at the cell edge when you are transmitting the first slot. Now when you are about to transmit in the second slot, before you come to that, you can actually do all the monitoring in the remaining time. Okay, so your mobile station will compute the power levels of the nearby base stations, and it will see whichever base station has the highest power, it will pick that. Okay, so by the time you have come to the second slot, maybe you are transmitting to base station B. So this is one advantage. It's called mobile assisted handoff. So since your mobile phone is doing all the computation during the remaining time, okay, and it is also assisting in handoff. See, now once mobile phone computes this information, it will now relay this information to the tower, to both the towers. Now then both the towers, of course there is also, once it goes to the tower, then MSN or mobile switching network knows, and MSN will say, okay, now why don't you switch, why not tower B take over the transition now? Okay, so then the handoff happens. So mobile assisted handoff, the handoff happens in a smooth way. Okay, so we don't have to worry about make before break and all those conditions. Okay, so in a make before break scenario, you have to first establish a connection and then disable it. So here you don't need to do all that. Okay, so then a mobile assisted handoff is possible only in digital systems, especially in TDMA was one of the big selling points for that we could actually do a soft handoff. Okay, now this is one interesting concept called the umbrella cell idea. So what do we mean by that is that sometimes you might have vehicles which are moving very, very fast. Okay, so normally then most of the devices, you see, cellular phone is designed for mobility, but not every device is going to move at high speeds. Okay, every mobile station is not going to move at high speeds. Now if you are going to move at high speeds, the problem is you have to switch your base stations frequently. You have to keep switching your base stations frequently. Your handoff has to happen very, very frequently. So every time there is a handoff that is happening, there is a probability that the call will actually get cut. Okay, there is a probability that the call might drop. Maybe your threshold is off, or maybe your MSN is taking long time. There is a delay in MSN to make a decision whether it has to switch to the base station or not. Okay, so there is a chance that a call there might be a drop in the call. So whenever handoff is happening. Okay, so that is why preferably if you want to minimize the number of handoffs, it is good. So that's something that cellular systems would keep in mind. Now the problem is, let's say we have a vehicle which is moving very, very fast. If it's moving very fast, then if the cell size is really small, then it has to do many, many handoffs. So then there's a very high probability that it's going to have a call cut. Okay, so we want to have a better user experience, which means we should not have any such broken calls or blocked calls. Okay, so instead what they do is that normally the regions will be divided into smaller and larger cell sizes. So first we'll have small cell sizes for slowly moving objects. So mobile phone, a pedestrian, a walking pedestrian and all that. And then we will have a larger cell. So for example, whenever you suddenly realize that, look, this mobile phone is moving faster, then the bigger base station will take over. You have a bigger base station and a bigger cell radius, which is only meant for high speed vehicles, which is only meant for high speed mobile stations. Okay, so this macro cell, so this is what we call as a macro cell, and this will be a micro cell. The smaller this is what we call as an umbrella cell. Okay, so we'll have smaller cell and one large cell called as the umbrella cell, and the tower is called the umbrella tower. That tower will cater to high speed vehicles. Now even if the cell phone is moving at high speeds, the handoff will happen at a less frequency because the cell size is really large, so it gets to spend more time within a cell. Okay, so this umbrella tower, which is going to radiate at a higher power, is dedicated only for high speed vehicles. Most of the pedestrian and low speed vehicles will be taken care of by the individual small cell base stations. Okay, the larger cell, this is called the umbrella tower or the umbrella cell, which is there. It will only see whenever you realize an object is moving faster, that information will be conveyed to the MSN, and MSN will probably order the umbrella tower to take over the handoffs for the faster moving device. So this approach of combining both, then I'll eliminate the problem of many handoffs for high speed objects, high speed mobile units. Okay, if your device is moving at a very high speed, you are moving on a car with a very high speed, you will still get connectivity because an umbrella tower will be connected to you. Okay, so this is it about brief ideas about handoff. I'll just quickly discuss a little bit about handoff in CDMA systems. So if you recall, in a CDMA system, we said that the CDMA uses the entire channel bandwidth, the entire band of frequencies to transmit. Okay, it uses the entire band to actually transmit data. It takes the whole band to transmit the data. The orthogonality is now entirely in terms of codes. Now let's say you have a mobile station which is operating on a CDMA standard, moves from one base station to the other base station. Now again, mobile phone has automatically computed RSSI. Okay, now since it has computed RSSI, now it knows that okay, I'm going to approach this base station. But then you can have some problems, as we said, whenever you're going to have a handoff, maybe your MSSN, either you have overestimated or there are chances that you might either have overestimated it or underestimated it. Okay, to avoid that, what normally in a CDMA system they can do is they can ensure really a soft handoff by ensuring that the second base station also transmits using the same code as the first base station. So the each user is uniquely identified by a code. Okay, and there are many users in this who have different codes. Now the second base station will use the same code that this base station, the first base station, has been using for this phone. So now the phone enjoys two signals coming, and they both are adding because both the signals are in fact same. So it will have very good call when it is actually transferring at the cell edge, because cell edge is when you start losing the call because your signal power is really weak. But then a CDMA has a very interesting advantage in that, because it's not going to use up any frequency. I mean, it's just the code is already not used by the users in this cell because every code is unique. Okay, so it will transmit data using the same code as this tower is using. Anyways, the frequency is same to begin with, so that way we can ensure a very soft handoff. So this was one of the big selling points for CDMA. Okay, because they wanted to show that its superiority in every way possible because it's a digital communication system. Soft handoff was also a big selling point for that. Okay, so again, this goes without saying, but if I have a CDMA system, if I quickly ask you what is the channel reuse factor, or what is the ideal cluster size of a CDMA system, it will be 1, because you end up using the entire band of frequencies for transmitting it, a CDMA signal. Because once you spread the bandwidth, you are going to spread the bandwidth. The bandwidth spread will be much more than the channel band, the low data. If you recall the CDMA lecture, I said you have a data rate which may be of the order of 9 kilobits per second, and it becomes several hundreds of kbps here. Okay, in fact it becomes megabits per second here. Okay, 1.22 and 1.25 megahertz is the bandwidth necessary to transmit. Okay, so now if you see, this is several orders higher compared to the input data. So which means it's going to take up the whole bandwidth of the standard to transmit the data. So that's why the reuse factor is just 1. So two cells are of course going to transmit in the same frequency band. The only difference is in their codes. Okay, a slightly more involved version of CDMA will be that now of course you will be given more band. You will not be given just 1 megahertz for transmitting. You will be given 5 megahertz or 25 megahertz for transmitting. The band will be 25 megahertz. So you can divide it into large chunks like this. Large chunks of bandwidth, say 1.25 megahertz. Okay, I can divide 25 megahertz of bandwidth, 25 megahertz of total available band into 1.25 megahertz chunks. Okay, so to further help a CDMA system in better combating interference, we can use one band for one cell, the other band for the other cell, so that there is some kind of frequency orthogonality, so these signals don't interfere with this. Okay, so I'll definitely discuss CDMA probably in upcoming lectures in more detail. You will see at that point there is something called coding gain. In the presence of channel impediments, like when the channels have finite bandwidth and all that, that's going to have an effect on CDMA. Okay, so we'll see what is that effect. So which is why using two different frequency slots helps. It at least helps in some parts. Okay, so I'll use frequency slot 2 here and usually different frequencies in other slots. Okay, so that's the only point which I wanted to talk about CDMA, that the handoff can be made really much more, it can happen in a way, the handoff can happen very subtly here in a CDMA system. Okay, both the transmit towers will transmit in the same code, using the same code, and that's like a huge benefit for the cell phone, because it can now exploit extra signal power in the same bandwidth. It's receiving extra signal power, so wherever the signal, especially at the cell edge, is when its signal power is going to go low. But now since two base stations are transmitting, its signal power will be good enough to give you good communications. Okay, so this is the soft handoff advantage of CDMA, and which was one of the selling points when it was competed against TDMA, the GSM second generation GSM phones. So this is it about the basics of cellular communications. There is only one point so far we have not covered, which is what we call trunking and grade of surface. Okay, so that I'll probably discuss in the another video. So what is trunking? I'll just introduce the idea of trunking in this lecture, and then we'll discuss about trunking in the next lecture. So in any communication system or a cellular system, once we divide it into cells, each cell, I said we are going to give k channels per cell, which means previously I said if it's an FDMA system, simultaneously only k users can be supported. But then if you actually see, the number of users in a cell will normally be much greater than k. Then how does the cellular system actually work? We'll have subscribers will be much more than the channels available. So then the natural question is, how does the cellular system work? If the subscribers are so high, how is it that so many users are able to make phone calls? Okay, so then obviously if let's say all the k channels are occupied, simultaneously k users are making phone calls, then you cannot, if a k plus 1 user tries to make a phone call, he cannot get the call through. Okay, the call will be blocked. Okay, so then how do you say whether the system is good or not? So how do you say, is there some kind of a metric which can tell me that okay, this k number of channels is really good for this cell? So I told you S is the total number of channels available, but how do you decide upon how many channels do we need at all in the first place? So if you recall what we discussed in the previous 2 to 3 lectures is that if I give you S number of channels and then you said okay, I'm going to use this and divide it into cells and so on, I'll come up with how many cells I need and all that. But then the question is, how many cells do we need at all in the first place? That is determined by the number of users you can support. Now what is the metric that we need to use to say okay, this is good, you can support so many users so well? So that we will discuss in the next lecture. So trunking and grade of service essentially talk about that. Okay.